危ないトラックが
Hey guys, welcome to eMaths. Let's do some maths for fun. Today, I will continue the quadratic series for part 3. In previous video, we have derived the quadratic formula by the method completing the square. And we know that it works for all quadratic equations. And we also mentioned something about imaginary number solutions. As I promised, in this video, we will be talking about imaginary numbers, nature of roots, and the discriminant b squared minus 4ac. Are you ready? Start! We will begin by solving a quadratic equation 3x squared minus x plus 5 equal to 0. This one looks so innocent, right? You might say, Teacher, I teach you. Take out a, b, and c, then sub into the formula. Now we need square root of negative 59. Press calculator. Square root negative 59. Wait, what? Max error. Never mind. We try using the graphical method. Wait, the graph doesn't even touch x-axis? Come to think about it, even if we square a negative number, it will still be positive, because negative times negative is positive. Maybe...
危ないトラックが
佐藤一馬さん、ようこそ死後の世界へ。あなたはつい先ほど不幸にも亡くなりました。短い人生でしたが、あなたは死んだのです。
We all live in a real world, and all the numbers that we encounter are real. No matter they are rational or irrational, they are all real numbers. However, far away, there's a world called the complex world. What's so special about them is that they are using the complex number system. The complex world is actually a nation of imagination. In this world, we have an imaginary number, which is the number I. This number I is defined such that I equals to square root of negative 1. So I squared equals to negative 1. To express the roots of negative numbers in terms of I, we can use the fact that negative p is negative 1 times p, and at the end, it is I times square root of p, where p is a positive real number. Because of this special I, complex number can exist in the form a plus bi, where a and b are real numbers. In a plus bi, a is said to be the real part of the number, where bi is the imaginary part. Complex number can be imaginary, where the imaginary part b is not 0, or it can be real, where there is no imaginary part. Imaginary numbers can be further divided into imaginary numbers and pure imaginary numbers, while real numbers can be rational or irrational. In short, when I ask pi to be rational, pi can just say, get real. Now what about operations in complex world? Well, for addition and subtraction, they are the same as how we do in the real world. Just collect the real parts and imaginary parts, like how we collect the like terms, and we are done. But for multiplication, it's a little bit different. This is what we do in real world. But in complex world, this is not true. For example, this is wrong. The correct way to do it is to use the definition of I from earlier. Before we go back to quadratic equation, we have to understand conjugates and division in complex world. Maybe not this conjugation in biology. I mean, conjugation of a complex number. By definition, conjugate of a complex number a plus bi is a minus bi. Together, they are called a conjugate pair. What is it for? Not like they can reproduce. When we multiply the conjugate pairs together, we can eliminate the imaginary part. At the end, we'll get a real number. If you don't believe, look at this example. 74 is absolutely a real number, right? In short, shit just got real. When we do division for complex number, because we don't want imaginary numbers to be in denominator, so we write in fraction form, then multiply by 1 using the conjugate of the denominator to form the symbol of 1. At the end, we just have to write in the form a plus bi, and we are done. Alright, Kono Subarashii no Sekai wa complex wo da yo. Okay, we can now come back to solve this. After a visit to complex world, we know that negative 59 is negative 1 times 59. And the whole thing is equals to I times square root of 59. Sub this into the equation. And finally, write in form of a plus bi, and we are done. Moral of the story, quadratic equation can have 1 real root, 2 real roots, or no real roots. To be precise, it's actually 2 real and equals roots, 2 real and distinct roots, and 2 imaginary roots. No matter what, there is always 2 roots for a quadratic equation. How do we know that? Still remember the quadratic formula? In this part here, b squared minus 4ac is what we call as the discriminant. If b squared minus 4ac is 0, because plus 0 and minus 0 both mean nothing. So the two solutions that we get will be the same. Do you see any I here? No, right? So it's a real number. Therefore, we call this 2 real and equals roots. If we plot the graph in real world, we can see that the graph only touches x-axis at one point. This is why sometimes we call it 1 real root. If b squared minus 4ac is a positive number, means the square root of it is defined. So we will end up with 2 different solutions. That's why it is 2 real and distinct roots. If b squared minus 4ac is a perfect square, then you will get a nice rational number solutions. If it is not, then you will end up with irrational number solutions. Finally, if b squared minus 4ac is a negative number, like the negative 59 earlier on, we will have no real number solution, but we do have imaginary number solutions. The third case is actually a little bit special, because the roots conjugate each other. This is because of the plus minus sign in the formula. For example, the question from earlier, x1 is 1 over 6 plus square root of 59 over 6i, and x2 is 1 over 6 minus square root of 59 over 6i. You can see there are complex conjugate pairs. To sum it out, if b squared minus 4ac equals to 0, then we have 2 real and equals roots. If b squared minus 4ac greater than 0, then we have 2 real and distinct roots. If b squared minus 4ac smaller than 0, we have 2 imaginary roots, which are complex conjugate. Lastly, I will show you some tricks about discriminant. We can actually use discriminant to find the distance between 2 roots. For example, for this graph of function fx equal to ax squared plus bx plus c, let the x-intercepts be x1 and x2. If we use the formula to solve for zeros, we have x1 and x2 like this. To find the distance between the 2 roots, I will use the distance formula from coordinate geometry, sub in x1 and x2, same denominator combine fraction, expand the bracket, square root and square can cancel, negative b and b can cancel, 2 and 2 cancel, and this is the distance between 2 roots, which is square root of b squared minus 4ac divided by a. Then what about midpoint between 2 roots? To find the midpoint, we just use the midpoint formula. Sub in x1 and x2. 0 divided by 2 is 0. Same denominator, combine fraction. Negative square root b squared minus 4ac and positive square root minus 4ac can cancel out each other. 2 and 2 cancel times 1 over 2. And this is the midpoint between 2 roots. With this concept, we can find the coordinate of vertex easily because the parabola is symmetrical about the vertex. The vertex and the midpoint will have same x coordinate, which is negative b over 2a. To find the coordinate of vertex, we calculate the x coordinate and substitute to find y coordinate. You will get the coordinate of vertex for sure. As for today, we have covered the complex number system, nature of roots, the discriminant, and we also use the discriminant to find distance between two roots, midpoint, and lastly, vertex of parabola. Finally, in the next part of the video, I will talk about the new method to solve quadratic equation. That's all for today. If you like this series, see you guys in the next video.